Hello and welcome back to Differential Equations, section 8.2 on solving differential equations using power series. So series solutions near ordinary points. Now, there is a whole theory of ordinary points. We are solving equations of this type plus some other function y prime plus yet another function times y equals 0. Now, when you divide everywhere by a of x to get your y prime alone, you can just define these other functions to be p of x y prime and q of x y equals 0. Obviously, you would divide this side by ax as well. You can't just divide one side, but yeah. And we have, these a, b, c could be any analytical functions, could be, like polynomial, exponential, and so on. And we take a look at the coefficients here, right, which are actually functions, and we try to figure out which points are good or not good. So if you generally have a denominator that would equal to 0, right, then for instance, you have, let's say, x minus 1 y double prime plus x cubed y equals 0, and you divide through by x minus 1 everywhere to get rid of x minus 1. Then you get your y double prime plus x cubed over x minus 1 equal to 0. And you take a look at this x minus 1 equals 0, which gives you x equals 1, right? So that will be the ordinary point. You can technically have that anywhere you want, but in not every case, right, this is going to happen. So you have to be careful. We are not going into this theory because generally the functions that we are going to consider are all going to pass the test for this, and we will be able to work these problems out and get a series solution. And we will be able to verify those answers as well, because we know other methods to solve these problems. Now, yes, this is a lot of writing, and yes, it's overkill for the problems that we are going to use it on. But please remember that this is like a sledgehammer approach. You use the sledgehammer when all other smaller hammers have failed, right? And even though sledgehammer can solve everything, right, you have to be very careful how you use it, right? So it's obviously going to be overkill to use a 40-pound sledgehammer to put a little nail into the wall to hang a painting or a little picture or something, because, right, you have to hold that very, very tiny nail and then somehow manage a 40-pound sledgehammer in your other arm to kind of hit it but not smash your fingers or something, so, or go through the wall to the other side. Right? So let's take a look at what we are dealing with in terms of the equations. So we're going to start with y double prime minus 4y equal to 0. Now, you guys know how to solve this, and you know the solution to this already, because that's your r squared minus 4 equals 0, r equal plus minus 2, your solution y is equal to c1 e to the minus 2t plus C2e to the positive 2t, and you are done, right? So this is your life from chapter 3, and that is not changing now at all. Oops. So what you need to do now is you need to learn how to do this problem using power series, and then we can compare the two solutions at the end. Now, how does that work? Well, if you remember the last class, we said that we're going to assume the solution of y equal function cn x to the n, and then we'll start at 0 and go to infinity. Then we'll differentiate that and get 1 to infinity cn n x to the n minus 1, and we'll differentiate one more time to get 2 to infinity cn n n minus 1 x n minus 2. And now, this is exactly where we ended the last class. You're supposed to plug these guys in and obtain something that is called a recurrence relation. And that recurrence relation will be the one that that you will be dealing with. Now, if you have this situation where you have x equals 1 and ordinary points and all that kind of stuff, well, in that case, you don't get to put x. You get to put x minus 1 to the n, x minus 1 to the n minus 1, and so on. So you have to be careful about these things. But as I said, this is our introductory lecture into power series. So even if it looks a little bit complicated and crazy, you have to understand that this is the most basic, simplest, never to see again cases, because the stuff that it's used for, right, is much harder, because this can be done right this way. So why would you spend a whole page of calculation or two if you can do it in 2 lines, right? All right, so instead of y prime, we have our summation like this, and then we have our cn n n minus 1 x n minus 2 minus 4 summation of 0 to infinity of cn x to the n equal to 0. Now, we need to put these two together, and the way to do that is to make them start at the same counter, and also have let them have the same exponent on x. Now, exponents not matching means that I have to do shift of the counter or peeling, right? Sorry, not peeling, shift of the counter. If the exponents match, you do peeling, because shifting the counter also changes the exponent, where peeling is only changing the counter and exponent doesn't change. So you have to be careful which way, right, you want to go. So if I go ahead and say this was, right, n equals 2 to infinity, and I subtract 2 on both sides, then I have that n minus 2 is equal to 0, and then I can call that k equal to 0, and from there I get the equation that k is equal to n minus 2, from where n is k plus 2. Now this is very important, because these are my substitutions that I'm going to use for each n that you see in the first sum. So we have summation, k starts at 0, goes to infinity, and then instead of having cn, I have ck plus 2. And then I have, instead of n, I have k plus 2, and instead of n minus 1, I have k plus 1, right? Because it would be k plus 2 minus 1. Let's write it that way. And then x, we know that n minus 2 is k, and then minus, this one stays exactly the same. If you want to bring this 4 in, you can, because we will have to anyway, eventually. So now, we're just going to simplify the first over here. So c, oops, it's supposed to be a k. I'm used to skipping some steps. We have k plus 2, k plus 1, x to the k, minus, bring the 4 in, 4cn, x to the n, oops, equal 0. Now, obviously, we can't put these together because these are k's, these are n's. So we can just rename k to n. And it's still the same problem. It's just now it's going to have n's, so we can combine it with the other. There we go. Now, I did have before questions from students which start with whoa, 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 whoa. You can't have k equal n minus 2 and then k equals n just to rename, right? And the answer to that is actually you can, but it doesn't make sense right off the bat. See, shifting the counter is not a transformation that you are taking into a different domain or different universe or anything like that, like Laplace, let's say, or U sub. Shifting the counter is literally shifting the counter. So the best way to explain why it is allowed is because you are actually dealing with two different snapshots in time between, let's say, ages of the same two people. If you say that mother and daughter have 20 years apart, 20 years apart, mother was 20 when she gave birth to daughter, whatever, doesn't matter. So if mother and daughter are 20 years apart in their age, so mother gave birth to a daughter when she was 20, then when mother is 20, daughter is just born. When mother is 30, the girl is 10. But see, the difference between them will always be 20 years. So when mother is 60, right, the girl will be, well, the girl, now the woman, it's 40, right? So the difference between mother and daughter is always, and that's a shift, right? That's a shift. It's a difference between two values, and no matter where you look, right, assign any age to mother, right, between 20 and, let's say, she dies 87 years old, doesn't matter, right? Any age that you pick up, the daughter will always be that age minus 20. So that's a shift, right? So if I look at this scale, and this is, let's say, I don't know, 2007, when mother was 20, right? And then you have 2008 and 2009 and 2010 and 2011 and 2012. No matter where you pick mother, the daughter will always be plus 20 to get to the daughter. But see, the trick is that all you did is you shifted the mother 4 units, and at the same time, because the same 4 years passed for the daughter, right, they're still 20 apart. So for shifting the counter, the thing is that these two, right, the y and y double prime, they are offset by 2 units. So I can go in and make this substitution and renaming, because all I am doing is I am moving along the same axis 2 units to the left or 2 units to the right, right? So that's all I'm doing. So that's why you can actually just rename k to n and then go back. These two equations are actually the same equation, just written differently, and that substitution throughout helped us with it. They add up to the same value. They look different, obviously, but they add up to the same value. All right, so now we get to the very important step of combining the two series together. And I said the two aspects that you have to have the same are the counter, right, has to be the same, and x to the n has to be the same. Now you can have x to the n minus 1, x to the n plus 3, right? You can have anything for that x to the n there, but it has to be exactly the same as the other one. And if it's not, your job is to shift the counter. And if you shift the counter enough to fix the exponents and the counters don't match, well, now exponents are fixed and you do peeling to match the exponents, to match the counters. But in our first, cheapest, simplest example, everything lined up as soon as we did our transformation there. It's not a transformation actually. As soon as we shifted the counter, everything lined up, and now we can just write one big sum for the entire problem. So here is the summation of n goes from 0 to infinity, and what I'm going to have here in this bracket is Cn plus 2, n plus 2, n plus 1, minus 4 Cn, and then all of that times x to the n, and everything equal to 0. So we were after this part here, right? That's the big part for us, which is what we call recurrence relation, right? Which is so hard to write on the elevated tablet because I have to keep that ice pack underneath it, and like when I have to write small, it's hard. So recurrence relation, and the problem is solved by figuring out that recurrence relation. I'll show you how. Now, please note that this is a sum. It doesn't play a role in this calculation here because you have two things that are multiplied, recurrence times x to the n. Now, since x to the n cannot be 0, right? Because if x to the n is 0, that means all x's are zeros. You're getting trivial solution to your differential equation. Your solution is garbage, right? So we don't consider that. Since x to the n must be different than 0, that implies that the recurrence relation has to be 0. Because you are multiplying two things into a 0, right? So if one cannot be 0, then the other one must be. Otherwise, the product would not be 0. And you can clearly see here that recurrence relation times x to the n is equal to 0. So, since x to the n cannot be 0, otherwise we're getting the trivial garbage solution, right, of all zeros, then we are having the left-hand side be 0. And now all you need to do is to solve that for Cn plus 2. Usually the one that has the highest, right, is the best way to go about. And that's obviously going to be Cn plus 2, n plus 2, n plus 1 is equal to 4 Cn. And then you divide by this one. So here is the Cn plus 2 is equal to 4 Cn divided by n plus 2 and n plus 1. This is the equation that you will always be going after when you are solving these series problems. And now all you need to do is to run all of these coefficients and see in which way these coefficients are related. Now remember, your sum starts at n equals 0. It will not always start at n equals 0. If you did some peeling, right, along the way to match the counter, it might start at 1, it might start at 2 or 3. So you are starting your calculations now at n equals 0, and I'll write it here because summation n goes from 0 to infinity 3 dots. So that's why you are starting with n equals 0. Now, we'll see an example hopefully later where you have to start with a different number. Now, when n is equal to 0, that means plug n equals 0 in there, you're going to get C2 is equal to 4C0 divided by 2 times 1, which is 4C0 over 2. Now you would say, cancel, cancel, cancel. Hold your horses, please. Let's not cancel anything yet, because we might need it not cancel. I'm not saying we don't, right? I don't know until I see it. Just don't cancel prematurely, right? Let's see what happens when n is equal to 1, n is equal to 2. We can stop at, let's say, n equals to 5. That should be good enough. So for n equals to 1, I have C3, right? And the C3 is going to be 4C1 divided by, when I plug in 1, 3 times 2. Because n plus 2 is 3 and n plus, right? You know what? I'm not even going to multiply this into a 6 or divide 4 into 2 and cancel. Now, I understand, right, that this might be inducing some anxiety right now, but, right, and you really want to do it, but let's just hold on for it, hold off just for a second. How about my C4, right? When n is equal to 2, 2 plus 2 is 4, so C4. That's going to be 4C2 divided by, and now this 2 is 2 plus 2, which gives me 4, and then times 3. Yes, I know that you can cancel 4 and 4, but let's not. What do I have here for C2 actually? Hold on. This is 4 over 4 times 3, and then C2 was 4 times C0 divided by 2. So this is 4 times 4 C0 divided by 4 times 3 times 2. Guys, I'm not really, hesitant to kind of cancel these values, because what I'm seeing here, if I put like times 1, I see 2 factorial on the bottom. I see 3 factorial on the bottom. Over here I see 4 factorial on the bottom. But if I do cancellations, I can't see any of those. So let's not, as I said, let's not prematurely cancel anything, right? Let me go with these calculations without canceling, because we have to observe the power series pattern if we are going to condense this back into a function that you are used to, like e to the x, sine hyperbolic x. It should spit out one of those functions. So, as I said, let's not prematurely cancel anything. Let's just go with it and see where it goes. How about n equals to 3? I said, well, let's go to 5 and see what we get. So C5, that's 3, 4, 5, it's going to be 4C3 over 5 times 4. Again, I'm not going to cancel anything, but now I have my C3, and that's 4C1 over 3 times 2. Ooh, 4 times 4, C1, divided by what appears to be 5 factorial, if I don't cancel anything. Obviously, if you cancel 4 and 4, you are ruining that 5 factorial on the bottom, and, such is life, right, after that point. N equals to 4, it's going to be C6, which is going to be 4C4 over 6 times 5, and that's 4 over 6 times 5. Now, what is my C4? Or C4 is this mess, which is 4 times 4 times C0 divided by, look at the piece of the puzzle for 6 factorial. Right? It just falls right into it, which is amazing. So I have 4 times 4 times 4 C1 divided by, and on the bottom I have 6 factorial. I'm still going to write it this way so we are 100% clear. Guys, I could have canceled a lot of stuff, right? I can cancel 4 and 4 and 4 with the 2 and 4 with the 6, but that would absolutely destroy my factorial on the bottom. So let's leave it. And we have a C7 now, which is 4C5 divided by 7 times 6. Oops, they're one apart. 7 times 6. And that's 4 over 7 times 6. And my C5 is this puppy here. So I have 4 times 4 times C1 divided by, oh, this was supposed to be C0. Yeah, that was C0. This is C1, and then I have 5 times 4 times 3 times 2, which is 4 times 4 times 4 C1 divided by 7 times 6 times 5 times 4 times 3 times, kill me now, 2. There we go. You have to do this every single time because you are looking for coefficients, and the coefficients will tell you, right, what you have at the end. Okay, now let's. This can continue forever. So you can do N6, N7, N8, depends on how much you really want to learn this so that when you actually see it in your field later on, right, whether it's exam, whether it's whatever class, homework, you don't freak out. And it is used. Again, what do we now have? Well, my solution, right, is the power series. Didn't we say that right here? And what I've done underneath is I just computed C0, C1, C2, C3. I got them all, right? So what I can do now is I can write out my solution using all of these C's. So my Y of T, let's say, is going to be, and now what I'm going to do here is I'm going to go and compute my summation. Remember, my summation was n starts at 0 to infinity Cn x to the n. Okay, when I plug in 0, I get C0 times x to the 0. Plus, next time around is a C1. Okay, C1, and then x to the 1. Plus, next time is C2. Okay, C2. No. Hold on. C2. Where is my C2? There is my C2. It's 4C0 over 2. Okay. 4C0 over 2, and then x squared, right? From the power series. You got to put this at the end. Plus C3. Well, that's on my list. C3 is 4C1 3 times 2. 4C1 3 times 2 x cubed plus. So you see that I'm just going through this power series here, and I am writing in all of these guys. So I had my n equals 0 term, n equal 1 term, n equals 2 term, n equals 3 term, and now it's time for n equals 4 term, and then n equals 5 term, right? Which is where I stopped with my terms up there. So what's my next one? Well, it's gonna be C4, and oh wait, C4 is so this is C0, C1, C2, C3, yeah, C4. So my C4 term is 4 times 4 times C0 divided by 4 times 3 times 2. Again, don't cancel. And then x to the 4 plus C5 term, which is 4 times 4 times C1 divided by probably 5, 4, 3, 2, 1. And then we have x to the 5 plus, and now finally these two that we actually see in our view, which is 4 times 4 times 4C0 over 6 times 5 times 4 times 3 times 2 of x to the 6. And the last term is the one that it's all the way on the bottom. 4 times 4 times 4 C1 over 7 times 6 times 5 times 4 times 3 times 2. Plus, it goes forever, right? It goes forever. Now, the question is, right, can we fix this somehow? And the answer is yes, we can, right? But what you see here is, I hope you see, right? This is now pattern recognition and why, right, certain students get to be in this class and others don't, Do you all see how each term has a C0 and each term has C1? Yeah, we're going to factor that. So y of t is equal to, I'm going to have a C0 party over here and plus C1 party over here. It's still the same term, it's just too long to put in one line. So what's my C0 party? It's x to the 0 plus 4 over 2x squared plus 4 times 4 over 2 times 3, or 3 times 2. I'm looking for 4 zeros. So that's a 4 0, that's a 4 0. Now 4 times 4 over 4 times 3 times 2, x to the 4. Good. And then this is 4 0 as well. Plus 4 times 4 times 4, C0 is kicked out, divided by 6 times 5 times 4 times 3 times 2, x to the 6 plus, and it's going to be infinitely many of them. And then plus, now I have to go and pick up all the C1s. That's x. Oh, I put x to the 0 over here. I should just put 1. I just put 1. Okay. What next? The next thing is to write x plus 4 over 3 times 2 x cubed plus 4 times 4 over 5 times 4 times 3 times 2 x to the 5 plus 4 times 4 times 4 over 7 times 6 times 5 times 4 times 3 times 2, and then you have x to the 7 plus dot 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 going forever. So this dot 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 contains both C1s and C0s, right? Which is why each one independently will get its plus dot dot dot, because they both have infinitely many terms. Okay, now is the time to just write what these functions are, and we are done with the problem. So what do we see as a pattern? We see as a pattern no 4, then 4, then 2 4s, then 3 4s. So that one should not be too much of a brain use. So we have this one plus C1 times this one. So if we are to combine this, well, clearly, oops, I put the summation and summation, right? So what do I have on top? Well, we see that we have 0th power for this. So we'll start at n equals 0, go to infinity because plus dot dot dot, right? And I clearly have 4 to the n on top because 4 to the 0 is 1, right? And then the next term is 4, which is 4 to the 1, and then 4 squared and 4 cubed and so on. So I have 4 to the n to start with. Then I am dividing that by, look at my factorials. The clear factorials that I see are 2 factorial, 4 factorial, and 6 factorial. Those are the ones that I see right off the bat. Well, looking at the pattern, this one better be 0 factorial. That looks like 2n factorial. When I start with 0, I get 2 times 0, which is 0. 0 factorial is 1. Awesome, fits the first term. Second term, n is equal to 1, right? 2 times 1 is 2. I get 2 factorial, which is 2. And then I get, next term is n equals to 2. 2 times 2 is 4. 4 factorial is 4 times 3 times 2 times 1. Awesome. And then a 6 and so on. And I also have this x to the 2n because I all have even exponents, right? So that's the top one. Bottom one looks the same, except it's all odds. And this should already be ringing the bell to you because we talked about certain stuff. I was about to say last semester, not last semester, last class. So you do the same analysis over here, and you see that you have this 4 to the n business, and if you start your counter at 0, 3 and then 5 and the 7, okay. So you have your denominators. This is your 1 factorial, 3 factorial, 5 factorial. You see, we never canceled anything, which is why we can see these things. If this was all canceled, it's like good luck. Because what would you do for 5 factorial if you're missing a 4 and 2? It would be like 5 times 3, and then the numerator, one of the 4, would be 2. Like, how do you put this into a 5 factorial? You don't. So that's why we don't cancel things. We just leave them around the way they are so we can make these claims. So the bottom is clearly 2n plus 1 factorial. And that takes care of that. Now, we have the exponents, again, 2n plus 1, because they're also 1, 3, and so on. So all we need to do is now figure out these 4s. So if we just put 4 to the n, then the first term is 0, which is 1. The second term is, well, yeah, 4 to the n. Good. All right. So we are able to put these together. And now the question is, right, what are these? What are these? Y to the t is equal to C0 summation n goes from 0 to infinity of 4 to the n x to the 2n over 2n factorial plus C1 summation n goes from 0 to infinity of 4 to the n x 2n plus 1 divided by 2n plus 1 factorial. So what are these? Well, there is one more step that we have to use in order to make this a little bit more accessible, I guess, or whatever. When you have your 4 to the n, you can write it as 2 as a 2n. And when you have 2 to the 2n times x to the 2n, you actually get 2x to the 2n. I'm not sure if you guys see that part. You should be seeing that part because that's algebra. It has nothing to do with calculus or anything like that. So I can rewrite this mess now as y of t is equal to C0 summation n goes from 0 to infinity, and then this becomes 2x to the 2n divided by 2n factorial, and the same thing over here happens, right? When you write this 2 to the n, 2 to the 2n, and then you have x to n, and then you just have times just x, which is that plus 1 that it's kind of peeled off. Then these guys combine right into the single one, and so on. So you're just going to get the same thing on the other side. So 2x to 2n plus 1, n goes from 0 to infinity over 2n plus 1 factorial. And now these are your basic functions. This is your c0 cosine hyperbolic 2x plus c1 sine hyperbolic 2x. Those are basic functions. When you have this even and odd split like this, when you have the even and odd split, then you just have these values. Cosine even is cosine, and this one is sine hyperbolic. And if they have alternation term in there like this, then it's regular sine and cosine, right? But without this term is hyperbolic. So they share the same formula because they're really, really close in terms of, right, the definition and everything else. So there is our solution, right? This is our solution. Now you will say, well, that doesn't look anything like what we had with C0e to the 2t plus, I mean, we used a, I think. Did I use C1, C2? What the hell did I use like an hour ago? C1 and C2. I don't care, I'll use C0 and let's use A and B, whatever. And you're just going to say, well, that doesn't look anything like that answer. Oh, no. It is exactly that answer. It's exactly that answer because we know from Calc 2 the definition of cosine hyperbolic and sine hyperbolic. And what is the definition? Well, your y of t is c0 e to the 2t plus e to the minus 2t over 2 plus c1 e to the 2t minus e to the minus 2t over 2. So how are you going to tell me that these are not the same? They are the same. Because now when I distribute all the c zeros and 2's and break them and collect the e terms, you get exactly this form. Now, a and b are going to be different coefficients, different numbers than c0 and c1. The question is just which form of the answer you want. Do you want exponential form or do you want hyperbolic form? But they are the same, right? The same thing, I can represent every sine and cosine wave using, instead of sine and cosine, using e, but I would have to use complex numbers within it. So it's not, So now we have y of t is equal to c0 over 2 e to the 2t plus c0 over 2 e to the negative 2t plus c0 over 2 e to the 2t plus c1 over 2, sorry, that's a minus, e to the negative 2t. And now when you collect these terms, you have c0 over 2 plus c1 over 2 e to the 2t plus c0 over 2 minus c1 over 2 e to the minus 2t. And here's your a and here's your b. That's how they're related. So it is, right, it is the same type of an answer. The question is just which form do you want? Actually, I can leave this. Say that's I don't know how to. Oh, I can do this. That's your A. That's your B. So you can have your answer in any form. Now, it was easy for us to, right, to observe that you have hyperbolic answers looking at the power series, which eventually turned into the sum of exponential answers. And those exponential answers are actually very hard to see in power series because one exponent was positive, one exponent was negative, and then they canceled, right? So that was a little bit, some of those terms canceled, so they're hard to observe. So this is what you would call the simplest possible and the straightforward problem in power series, where and every single problem is the same, right? You first write your derivatives down, then you stuff everything into differential equation, and then you match the terms. Match the coefficients and the exponents. So you either do shifting or peeling or both, depending on a problem. That gives you eventually, right, when you combine everything, gives you the recurrence equation. Recurrence equation you solve for the largest Cn plus whatever value, which is the red box right there. And then you just work out a couple of these, 4, 5, 6 of these. I worked out 6, which allows us to uh, write out the solution. Now, guys, this is already your solution. Like in engineering, you would not actually go and do any of the math below, because you already have the power series, and power series is very, right, it converges to the solution, and it's very, very accurate. Only even if you just using like first, 4, 5, 6 terms, it's very, very accurate. So for purposes of engineering, and you don't have such a close, tolerances and so on, like literally this is where you stop. And it might be even overkill to compute this many terms at the first time if you just need to compute certain part of, I don't know, maybe you're working energy storage, like literally anything, whatever. All right, so we got the solution, and we got the solution to match exactly with what we had over there. So now let's take a look at a different solution, which will cover the wave sign of things, right? Us hoping to get that trigonometric answer, because if I want to work on oscillations and things, it's going to be trig, which is all alternating currents, springs, rubber bands, pendulums, right? It's all going to be that. And don't you love it when your most basic example is like 2 pages already? So how about y double prime plus 9y equal to 0? So this is the problem we actually did last class. I said, right, we start by assuming Cn x to the n. Then y prime is going to start at 1, get Cn n x to the n minus 1. And finally, the second derivative, summation 2 to infinity Cn n, that's n minus 1, and then x to the n minus 2. So this is what we have, and now we plug everything in. And this is not going to be any different than the previous example. The Cn's are going to work out a little bit differently, obviously, but not a big deal. N minus 2, and you're going to have plus 9 summation Cn x to the n equal to 0. So now, when we shift the counter, it will add 2 to all of these. I'm just going to say shift counter, and when you skip those steps, you get Cn plus 2, n plus 2, n plus 1, x to the n plus 9, and then you have your summation 0 to infinity Cn x to the n equal to 0. So summation 0 to infinity of Cn plus 2, n plus 2, n plus 1 plus 9 Cn, all of that times x to the n equals 0. Now since x to the n cannot be 0, then Cn plus 2, n plus 2, n plus 1 plus 9 Cn must be equal to 0. And you're probably thinking, like, how's this problem any different than others? We just have a 4 right here. No, you actually have a plus there as well. Earlier you had the minus there. Because now, when you solve for Cn plus 2, you're going to get negative 9 Cn over n plus 2, n plus 1. And that is a big change. Like that one sign right there determines whether you have trigonometric or hyperbolic answers. And it's a big deal. You will say, you mean exponential answers? Yeah, exponential answers are just little convenience for your chapter 3, so you don't go crazy with hyperbolic functions in there. But it's supposed to be actually hyperbolic because the world is divided between hyperbolic answers, which are not periodic, and trigonometric answers, which are periodic. And that e-convenience is just an e-convenience, right? That's all it is. Actually, when I learned differential equations, my chapter 3, we had to convert every exponential answer we get into hyperbolic answers. I didn't have you do that even once because I'm a terrible instructor. But when I learned this, my professor was requiring every solution in chapter 3 when you had whatever e to the blah, 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 to be converted into hyperbolic answers at the end. And then when he hit us with power series, it all clicked immediately, and it was clear that the world of differential equations in the second order case has either hyperbolic answers or trigonometric answers, and none of that e stuff was floating about as a third wheel, because it can be converted into easily, right? It can be converted. Anyway, going back to our problem over here, our class, we have the cases now. So our thing still started at 0, so n equals 0. We don't need to be dramatic. So n equals 0. Plug n equals 0, you get C2 as negative 9 C0 over 2 times 1, so just 2. When n is equal to 1, you get C3. That's negative 9 C1 divided by 3 times 2. Ooh, we are already developing factorials. You need to pick that up immediately. C4 is going to be negative C2, negative 9 C2 over 4 times 3. But hold on, right? It's negative 9 divided by 4 times 3, and your C2 is negative 9 C0 over 2. Awesome. 4 times 3 times 2. There's my factorial right there. But look at the top. Negative times negative will be positive. So this one is negative. That one will be positive. And you can see that alternation, because remember what I said before, the only difference between hyperbolic power series and trigonometric power series is the only difference is the alternation. So because this is a plus 9 to the n, and that's going to be minus 9 to the n, there's your alternation, and you are going to have the that negative 1 to the n term, which gives you trig. So the problem works exactly the same as the previous problem, except this one will have alternation. So this is going to be positive 9 times 9 C0 over 4 times 3 times 2, which is a 4 factorial. So n equals to 3 gives us a C5, which is negative 9 C3 over 5 times 4, which is now negative 9 over 5 times 4 times C3, which is negative 9 C1 over 3 times 2. And that is equal to positive 9 times 9 C1 over 5 times 4 times 3 times 2. And C6 is going to be negative 9C4 divided by 6 times 5, which is negative 9 over 6 times 5, and then negative, no, lies, C4 is 9 times 9, C0 over 4 times 3 times 2, and as you can see now, we're back to negative. So if you're looking at the C0 terms, look at the top, negative C0, positive C0, negative C0. So it's alternation. It jumps from one to another. So once we split it up later, we'll get that. N equals to 5, the last one, C7 is equal to negative 9 C5 over 7 times 5. Again, we can go with this, waste all day. Oops, 7 times 6 there. And C5 is 9 times 9 times C1 over 5 times 4 times 3 times 2. There you go. So your solution of y of t is simply when, remember your power series? I don't even know where to squeeze that thing right here. It was summation 0 to infinity of Cn x to the n. So when you have a 0 across the board, it's just C0 times x to the 0. Then the next term, C1 x to the first power, but I don't want that confused with the derivative, plus C2. Okay, I got the C2. C2 is negative 9 C0 over 2 x squared plus negative 9 C1 over 3 times 2 x cubed plus now we have 9 times 9 over 4 times 3 times 2 x to the 4 plus 9 times 9 over 5 times 4 times 3 times 2 x to the 5 plus negative 9 times 9 times 9 divided by 6 times 5 times 4 times 3 times, kill me now, x to the 6 plus negative 9 times 9 times 9, oops, I forgot my C0s, what the hell, C0, C1, C0, C1, there we go, and then 7 times 6 times 5 times 4 times 3 times 2, x to the 7 plus 3 dots because it goes forever that way. All right, we collect like terms again. So C0 times blah plus C1 times the rest of the blah. So that's 1 minus 9 over 2 factorial x squared plus 9 times 9 over 4 times 3 times 2x to the 4 minus 9 times 9 times 9 over 6 times 5 times 4 times 3 times 2. You know what? That's a 4 factorial. That's a 6 factorial. X to the 6 plus 3 dots going forever. Plus C1 is x minus 9 over 3 factorial of x cubed plus 9 times 9 over 5 factorial x to the 5 minus 9 times 9 times 9 over 7 factorial x to the 7 plus going on forever there. And there's your answer. You have C0 summation 0 to infinity negative 1 to the n, and then you have your good old 9 to the n, and then x to the 2n divided by 2n factorial plus C1 summation 0 to infinity negative 1 to the n, 9 to the n, and then x to the 2n plus 1 over 2n plus 1 factorial. You use the same trick with the 9 where you write 3 squared, right? So if you write 3 squared raised to the n, you get 3 to the 2n, and then you can combine that with the other x. So y of t is equal to C0 summation 0 to infinity of negative 1 to the n of 3x raised to the 2n over 2n factorial plus C1 summation 0 to infinity of negative 1 to the n of, again, 3x 2n plus 1 divided by 2n plus 1 factorial. This puppy over here is your cosine. So y of t is C0 cosine 3t, and I used x's. Y of x, y of x, y of x, cosine 3x, because I can't get t when x is in the power series, plus C1 sine 3x. That's it. There it is. Is this correct? Well, hell yes, because y double prime plus 9y equals 0 is giving you r squared plus 9 equals 0, and r is equal to 3 plus minus 3i, right? So you know that those are the coefficients. And we did not have any dampening, so that means that there is not going to be an exponential function in front to kill the oscillations. So this will be oscillating forever, right? Because there's nothing to slow it down, change its energy state or anything like that. So it just goes and does what it does. So this was a trig example, right? And as you can see, it's exactly the same basic example as you had before. Now, will you ever be, are you always going to be able to compress this into what you would call a nice function at the end, right? Can you always compress your answers into trig and exponential and hyperbolic and all that stuff? And the answer is hell no, you can't. In which case you leave your answer as a power series. Because, again, remember, this is a sledgehammer. This is a sledgehammer for all jobs, house related. From framing it for the first time all the way to putting the nail into the wall. If you had to break some concrete or rocks or something, a sledgehammer is used. You can't use a small hammer or nothing. But if you are very careful and very strong, you can also use the sledgehammer to put the painting up on the wall. And that's exactly what you guys see in this problem here, right? Me wielding a 40-pound sledgehammer very carefully, okay? Very carefully. But we got the same answer at the end. So, and we check. In both cases, we checked. And up there, when it didn't look like we had the right answer, I did the conversion to show that the answers are the same answer. Yeah, so it's all fun and games until we run into problems that are not this straightforward. Will I call it easy? Well, maybe when you do a couple of these problems and you don't have to worry too much about it, right? It's definitely on the spicy side, a lot of things to follow and try and test. And, you know, working out 5 homework exercises might not be enough to kind of put you at the level at which you would like to be, right, for this. But there is, right, a whole bunch of situations, right? There are, not is, are, a lot of situations where you cannot simply just do what we did here and compress it all back into your trig functions. You actually have to suffer more, and then you can't. In many cases, you can't even make a function out of it. You just leave it as a power series, which is fine, right? Your solution would be, in that case, a polynomial. Yeah, rejoice, right? Woohoo! You won in life because you have a polynomial, which is the answer to your differential equation. Well, that's easier to compute than exponential trig functions, than hyperbolic functions, right? It's easier to compute polynomial. So maybe, as I said, as engineer, right, take the first, 4 or 5 terms over here and compute your values in there. Because it already provides really, really good what do you want to call it? Exercise? Whatever. Okay. Now, speaking of evil stuff, we want to take a look at some problems that are not constant coefficients, right? Because again, you ought to be using sledgehammer for the jobs that the sledgehammer is designed for, right? And a small hammer would not work there. Something like problem number 6. Lock the doors. X squared minus 1, y double prime, minus 6xy prime, plus 12y equals to 0. So, but we have to deal with it. It's okay to have that emotion. You just have to deal with that. So you'll see this one, right? The rest, not so big deal. A little bit of peeling here and there, right? We're done. This one. Let's go. Y is our standard Cn x to the n, starting at 0. Y prime starts at 1, Cn n x to the n minus 1, and y double prime starts at 2 to infinity, Cn n n minus 1, x to the n minus 2. So what do I have? X squared minus 1 summation of Cn n n minus 1 x to the n minus 2 starts at 2, minus 6x, so we start at 1, infinity, Cn n n x to the n minus 1, and then plus 12, summation Cn x to the n equal to 0. That's 0 to infinity. All right. So this problem would just be a simple peeling problem. Do you have a simple peeling problem? You don't. I don't know why in this book there is no a simple peeling problem, but there is one. Okay, fine. Look, when this x goes inside, and it can, because remember, summation operates on n as a variable, not on x, so x is free to go in and out. See, this x is trapped because it's x to the n, and summation operates on n. But the x in front can go in and out. And when x in the front goes in, it makes that x to the n, which matches this one. Same thing with this x squared. When it goes inside, it will kill -2, and then you will have x to the n across the board, and you can just fix the front coefficients by, counters by peeling. This one, right? Because that one will introduce, again, shifting. Now let's take a look. You have your x squared times the summation Cn n n minus 1 x to the n minus 2 minus just the summation 2 to infinity Cn n n minus 1 x to the n minus 2. And you can see now you have nothing to balance it with over there. Right? So yeah. And then you have minus your 6x summation Cn n x n minus 1. That starts at 1. And finally plus 12 summation 0 to infinity Cn x to the n equals 0. Oh, did I mention turn your notebook sideways? I didn't, right? Yeah, right. At this point, I should be somehow separating these steps. So these are all, one expression. All right, so now the x squared, I'm just going to do the orange thingy, is going to go in. The x is going to go in. And we're just left crying right there. So you have a summation 2 to infinity of Cn n n minus 1 x to the n minus summation 2 to infinity Cn n n minus 1 x to the n minus 2. And then minus, you can pull the 6 in as well, obviously. It's just going to be summation 6 Cn n x to the n. Again, right? So we don't have any issues there. And we still have our plus 12 summation 0 to infinity Cn x to the n equal to 0. So I need to shift this one. Let's put a sad face there. How about no face? There we go. So we got to shift that one. Okay. Well, we kind of learned, right? Shifting, it's just going to bump everywhere plus 2. So summation 2 to infinity Cn n n minus 1 x to the n, and then minus summation 0, right? We shifted that because I have to shift to line up x to the n as well. So infinity right there. Now we have Cn plus 2, n plus 2, n plus 1. This is the same shift as we had earlier. So I'm just flying through it. Minus summation 1 to infinity 6 Cn nxn plus put 12 inside, summation 12 Cn x to the n equals 0. This is 0 to infinity. When, let me separate the steps again, and I'm going to write this in blood. When x to the n match in all terms, peel, do not shift. Because if you shift to match your counters, you're going to mess up exponents. Because they're always linked through the same n. So if you fix one, you're going to mess up the other one. So as soon as one of these lined up, like people that did the Rubik's Cube, they know exactly what the pivot corner is. Like you don't mess with that. So you have x to the n, and it's matched in every term. So now, since they're all across the board, you will just say whichever one has the highest counter is going to become a base for my problem. And that's 2, which means first is going to survive the way it is. Now, if this doesn't make sense after I do it, it's YouTube video. It's time to kind of rewind it 15 times until you get it. I can't learn it for you, right? Minus, this is where the peeling happens. I have to peel off n equals 0 and n equals 1 so my sum can start at 2. This is why, right, peeling can only peel terms up to a certain number where you want to stop, which is why you are looking for the highest value, and that's going to be your target. And you have to peel in every other term, in every other sum, you have to peel up to that number. So when I peel n equals 0 from here, right, that's going to be C2 2 times 1, and then x to the 0 is also 1. I'll actually write it as x to the 0. There we go. Then I need to peel another term, and it's also going to be negative, obviously, because negative distributes into each term. Now I'm peeling 1, and that's a C3. And then it's 3 times 2 and times x to the first power. And now minus the rest is the summation that starts at 0, and I have Cn plus 2 n plus 2. Oh, there's no room. This might be a three rows over here. I don't want to generate. I know I can generate space this way, but then that messes up if I'm exporting this. So 2 infinity Cn plus 2. I don't see the problem. It's right there. Cn plus 2, n plus 2, n plus 1, x to the n. Good. Minus, over here I just have to peel one of these guys. So it's going to be 6c1 times 1 times x, and then minus the rest stays as is, but it starts at 2, which is good. And finally, we have plus. I have to peel 2 of these, so that's going to be 12 C0s, x to the 0, plus 12 C1s, x to the 1, plus the rest of the series will start with 0. If you are having headache from this, shake it off. What can I say? Right? This is all one expression that goes into three rows. So now, what are my non-sum terms? Well, I have 12c0 plus 12c1x. I have minus 6c1x. I have minus 2c2 and minus 3c3, no, minus 6. 2 times 3 is 6, minus 6c3x. Plus, and now I'm going to put one big fat sum over here for all of the other ones, because now they match, the counters match, and their x to the n matches. I don't need this one, this is a repeat, because I started in the next row. Yeah. Okay. Guys, I removed this part here, because it was just this much written. I forgot to remove it when I decided to go to the next row. So make sure you don't have, make sure it was this. This was written. Make sure you remove it. Make sure you kill this. All right, so what do I have inside? I have Cn n minus 1. I have minus Cn plus 2, n plus 2, n plus 1, minus 6Cn times n, plus 12Cn. X to the n equal to 0. All right. What is all this mess? Well, we definitely have our recurrence relation there. It's just good luck with it, but we have one. And you have your stuff that it's already the part of the solution up there. We'll see how that comes into play. So the first part on top equals to 0, recurrence equals to 0, and that's going to give us a whole bunch of equations that we can work with to come up with this stuff. Now, let's go and deal with Cn. You know what? N squared minus n minus Cn plus 2 with n squared plus 3n plus 2 minus 6 Cn times n plus 12 Cn equal to 0. That's the highest one we're going to solve for. So Cn n squared plus 3n plus 2 is equal to, and then you put all of these to the other, so you move this one, right? So when you move this one and it becomes positive, then all the other ones stay as they are in terms of sign. So this is Cn n squared minus n minus 6 Cn times n plus 12 Cn. And finally, we have Cn, oh, that was Cn plus 2. I was like, what the hell? There we go, Cn plus 2. Cn plus 2 is going to be this whole thing which can be simplified, obviously. You see, when you factor out Cn over here, what's left is n squared minus n minus 6n plus 12. And on the bottom, you just have n squared plus 3n plus 2. So the top gets simplified into Cn times n squared minus 7n plus 12 divided by n squared plus 3n plus 2. Now, there are numbers which are n minus 3 and n minus 4 that factor on top, and the numbers that factor on the bottom are n plus 1, n plus 2. So that doesn't have, but it helps us in calculations, obviously, because why would you do the squares and sevens if you can just add and subtract in linear terms? So Cn plus 2, as you can see, it, dare I say, beautifully simplifies into n minus 3, n minus 4 divided by n plus 1, n plus 2. So that's our life now. There we go. That's your recurrence relation, RR. You know what goes. N equal to 0. Yeah, we're nowhere close to being done. Except we're not going to be able to find those compression functions for trig and stuff like that. We'll have to leave it as a polynomial. Anyway, what do I have here? Ooh, guys, terrible, terrible, terrible me. N equals to 2 because summation 2 to infinity. See that? I made a mistake. Right? Do we all agree that the first n you can use for recurrence relation is 2? Right? You have to be careful about those things. It's not automatically n equals 0. So n equals 2, the first number you get is going to be C4. Right? And you're going to go, C4, where are there C0, 1, 2? They're right here. C0, C1, C2, and C3. You see that? They're already taken care of. They're already taken care of. Your job is to get C4 and on. Okay. Well, what's the C4? It's going to be C2. And then when I plug in 2, I'm going to have negative 1, 2, 3 times 4. And now, since we're not going to be looking for any of those functions, this is going to be negative C2 divided by something, whatever the hell is going to be divided by. 6. There we go. Negative C2 over 6. N equals to 3.
It should be positive, right? Because I think you just missed the negative. Where n minus 4, then you get...
Oh, thank you.
Yeah.
Okay, you're right. N minus 4, that is 2 minus 4, which is negative 2, and then negative 2 times negative 1 is positive 2, and then 2 will cancel with 4. All right. Oh, it's just so easy to make mistakes here. C3, and look what we get. 0 times 1 over blah, because that's going to be a big fat 0 there. N equals to 4 is a C6, and that one also works out to be 0. Because you gotta have n minus 4 up there, 4 minus 4. N equals 5 is going to be C7, which is going to be C5 times, that's a 5, so that's going to be 2 times 1, right? 2 times 1 over 6 times 7. But hold on, C5 was 0, right? So that's going to be over 2 over 42, and that's also equals 0. Ooh, looks like all of these guys are zeros. So you're going to say, so what's left in my life? Well, all of those terms that you have in front, right? That's all in your life. These things. And I'm not copying those. I mean, I am copying them literally. There we go. And then over here at the end, I will have this one, C2 over 6, with the x squared on it. Right? So, oh, actually, no. I skipped something and then messed it up. Delete this, burn the page. Delete this and burn the page. We're not done yet because I have... Do we have time? Another 15 minutes or so? Or actually 7 minutes, but whatever. We'll finish it off first. What we're going to do now is we're going to... Come on. Bring this back in. There we go. And we're going to set this equal to 0, right? Because the top is 0 plus 0 equals 0. When I go back, because we use this recurrence, right? And set this one equal to 0 times a non-zero gives us 0 for the whole term. But in order for 0 to be added to this has to be 0 as well. So we set that one equal to 0, and we solve that one for C3. And we solve it for C2. And we do have relation that C4 is C2 over 6. So that's going to be introducing that one as well. Okay, so solve this for negative C2. When you bring it to the other side, becomes positive, is equal to 12C0 plus 12C1x minus 6C1x minus 6C3x. There we go. Divide everywhere by 2. So C2 is equal to 6C0 plus 6C1x minus 3C1x. Why am I not combining these two? That's a 3C1x. If I copied everything correctly, because there's just so much. There we go. Nope, that's not it either. Guys, I'm fried. This is my second class, and I've been constant on 4 hours, and this stuff is way too much. I need to like take a deep breath. Partial fraction decomposition method trick. Coefficients of x's will be equal to 0. Coefficient and the constants will be equal to 0, which will give you relationships between the values that we need. There you go. So that's on the third try. I finally got it. So I have these guys. Those are the x's. Now these two combine. So I have 6c1x minus 6c3x, and then plus 12c0 minus 2c2 equal to 0. Now this is 0x plus 0, if you want to write it that way. So let's go. Blue equation is 6c1 minus 6c3 is equal to 0, from where we find out that c3 is equal to c1. And the red equation, which is this, is 12c0 minus 2c2 is equal to 0. When I move c2 to the other side, it becomes c2 is 6c0. You should check that, because, as I said, I'm fried. I'm gone. Okay. Now we can start writing our y of x solution. Remember, my power series was 0 to infinity cn x to the n. So I have c0 plus c1x plus c2x squared. You know what? I'm just going to write c3x to the 3 plus c4x to the 4 plus, and I'm just going to quit. So now y to the x is c0 plus c1x plus, instead of c2 I have 6c0, and that's x squared, plus c3 is just c1 x cubed, plus, you remember that we had c4 up there, which is c2 over 6. but then C2 is 6C0, and then this is just C0 x to the fourth. Now, we calculated that all other coefficients are 0, so the solution stops there. And all I need to do now is to collect, because remember, all of your solutions are always like A times blah plus B times blah, or C1 and C2, or whatever you. Now we're going to have C0 and C1. So all I need to do is to factor out C0 and C1, and the semester is over. So dramatic. So C0 gives me a 1 plus 6x squared plus x to the fourth, and then plus C1 will give me x plus x cubed. Box this and walk away. There we go. Wow. Exactly at 12:50. So I hope that at least some of this made sense. You have seen the sledgehammer. I will just quickly repeat over here where this problem we did it, right? Everything started the same, and this time it will be so easy and nice without this one. We wouldn't have to do shifting, right? We could just peel and be done. But when we pull in x squared, it fixed our exponents to be xn everywhere except this one, which is why I wrote we have to shift that one to fix the exponents to match. Well, once we shifted that one, we had the matching exponent, but now we do not have matching guys over here. And I said when x to the n matches, in all terms, peel, do not shift. So you pick which is the highest one, in our case is 2, and then you make every single one of them start at 2 by peeling 0 and 1 term, whatever is necessary. So looking at the first one, that starts at 2, so that was just a copy. These two terms here are 0 and 1 terms from this series. So those are the ones. And then you can see that exactly the same series here is the same as this one. It just starts at 2 because we peeled off n equals 0 and n equals to 1. We peeled those terms out, and you're just left with the rest of the terms. So we repeated the same procedure in all of these other ones. So this is your n equals to 1 term that we peeled from this one, and then the rest of the series starts at 2. And we peeled off n equals 0 and n equals 1. Maybe I should just color code these. I'm just going to put a blue star over here, and this was a purple star over here, and the red star over here. So we peeled those terms, and they're color coded, as you can see now, to match those colors. Once you peel those terms, put those terms in front, you have the series now. You can combine it, you can recurrence, solve the recurrence for the highest, in this case n plus 2, go through the procedure for recurrence the same way we did, and then when you're done with that, and we were kind of quickly done with it, right, because they just started being 0. Setting your the terms that you peeled, you set those equal to 0, and then you use that trick from partial fraction decomposition. And that's it. So you can go back and rewatch the video. So there's your 2-hour class. We did 3 examples, and you have like 15 pages, right? And probably a headache. So it's time to actually use this especially when someone says, "Ah, what do you know?" Well, pull this up and explain. We have one more class on Monday, so I will see you then. Bye.